Hello everyone, I am Jane and I am going to present Tnt-LLM, text mining at scale with large language models. So basically Tnt-LLM is a framework designed to address one of the core challenges in text mining, balancing quality and scalability. So let's check why this is so important and how Tnt-LLM makes a difference. So first let's talk about the problem. In text mining, the goal is to turn unstructured text into structured, meaningful insights. Traditionally, this requires either manual creation of taxonomies or like automated clustering. Both approaches have major drawbacks. Uh, manual taxonomies are like time consuming and require expensive domain expertise. Automated clustering, while faster, often produces results that are hard to interpret and less useful in real world applications. So this is where Tnt-LLM comes in. By leveraging the power of LLMs, the framework combines the human-like ability to understand context with the speed of like automated processing. It is scalable and efficient. So next is system architecture. Tnt-LLM achieves the like balance of quality and scalability with a well-designed system architecture. It consists of four key components. The first one is text summarization module. This pre-processes the data by summarizing it into concise, like meaningful snippets. And then comes taxonomy generator. This is where the LLM creates and refines the label taxonomy iteratively. Data labeling system. The LLM uses the taxonomy to label large data sets. Like generating what we call pseudo labels, and then lightweight classifier. Finally, these pseudo labels are used to train efficient classifiers that scale well in real world applications. The good thing in this design is that each component can be optimized independently, so we can continuously improve the system without disrupting the like entire workflow. And next comes technical implementation. So Tnt-LLM employs principles of like stochastic optimization, like how neural networks refine their parameters during the training. The system iteratively improves the taxonomy by processing the data in batches, so which allows it to adapt as it encounters new information. Its specifications are a batch size of 200 conversations per iteration, parameters nu sigma, which represent the taxonomy structure, and tuned temperature settings like zero point 0.5 for generation and zero point 0.2 for updates to maintain a balance between the creative side and the stability side. And next comes the experimental setup. The framework was tested on a conversational data from Bing Copilot, a multilingual AI chat system. This dataset was chosen because it reflects the real world no, diverse interactions across multiple languages and domains. The dataset was split into two phases. Phase 1, where 9,592 conversations were used to develop and validate the taxonomy. And in phase 2, 48,160 conversations were used to test the framework's scalability. The framework tackled two tasks. The first one is intent detection, like classifying user intent into 10 categories like advice seeking or technical support, etc. And the next one is domain classification, Here, organizing conversations into 25 different broader categories like health or finance or travel, etc. And then comes evaluation metrics. To evaluate TNT LLM's performance, we used a combination of technical and practical metrics. Like first one is coverage, where we measure whether all the data points are categorized or not. Label accuracy, assessing how well labels match the text, and the inter-rater reliability. Comparing the system's results to human judgments. So by using these metrics, we validate both the technical robustness and the practical utility of the framework. Next is ablation studies. Uh, these provide valuable insights into what makes the framework work so well. The first is LLM choice. GPT-4 significantly outperformed GPT 3.5 Turbo in intent detection, where deeper reasoning capability is required. For simpler domain classifications, the performance gap is narrowed, like making GPT 3.5 a cost-effective alternative. And the second one is embedding models. The ADA2 embedding model showed a strong multilingual performance, indicating that it captures universal semantic features effectively. So these findings highlight how different components contribute to the system's success. And next is the performance analysis. Tnt-LLM delivered exceptional results in both coverage and accuracy. The key metrics include intent accuracy, which is 0.746 for English and 0.725 for non-English. Domain accuracy, 0.733 for English and 0.673 for non-English. Latency, it's 100 ms per classification, which is very low. These numbers show that the framework is not only just efficient, we can say, it's producing results that align with human understanding. And the next is scaling characteristics. Instead of using LLMs for direct classification, Tnt-LLM uses them to generate training data. This approach reduced the computational cost by 85% compared to a full LLM deployment while maintaining that comparable performance. The system can process 10,000 texts per minute in batch mode and under 100 ms per text in real-time applications, which is a very low latency. This makes Tnt-LLM a highly practical, better solution for large-scale text mining. And these are the references of the paper. Thank you.